Okay, so what is it all about? Well, let's explore this example here. We use the Euclidean distance, but just that you know, all what we discuss here also holds for most other distance measures. So consider two-dimensional vectors A and B. So A is here, B is here. The Euclidean distance between A and B is the C here, yeah, which can be computed like this one here. So it's the square root of 10 numerically. Which corresponds to the norm of the difference vector C. So this is the vector between A and B, which can be projected down here, and this is the length actually. So that the distance between A and B is the length, which is usually computed by the norm of this vector here. Yeah, so the norm is the same as here. Yeah. Okay, so have a look at the norm. With increasing dimensionality, the distances or the norms grow too. Well, that's somehow, as I said before, trivial, but what does it mean? So example here, in the two-dimensional case, the distance is 10. So now double the feature vector length with the original features. So now let's have not two-dimensional vectors but four-dimensional vectors with just doubling the features. So instead of 1 2 we have 1 2 1 2, and instead of the point B 4 3 it's now 4 3 4 3, and we see that the norm of this difference vector, which is the distance, the L2 distance, grows correspondingly from square root of 10 to square root of 20. And now you can also say that, well, of course, the fact is probably not so important because, well, we just have more values. So more values now contribute to the distances, to the norm. So that's just a matter of a larger scale, isn't it? Well, no, it isn't, because we will see that the contrast also of distances is lost in higher dimensional data, because the distances grow and they grow more and more alike. And we will have a look at on the next slide why this is so. And this is known as the so-called concentration of distances. So first of all, we say, okay, we agree that the distances grow. So what does this have? What impact can we follow from that? And that is this concentration phenomenon. So as dimensionality grows, distance values grow, okay, and they grow such that the contrast provided by usual measures decrease or even diminishes. What does it mean? Well, it means that the distribution of norms in a given distribution of points tends to concentrate. Well, again, what does it mean? It means that the distances you can compute between two arbitrary points tend to become more and more similar. So you cannot distinguish between different pairs of points just because of their distance, because all the distances are more or less the same. Yeah? And to illustrate that, we have another example with the Euclidean norm. The Euclidean norm of vectors consisting of several variables. We assume that those variables, the features, are independent and identically distributed. So all the features here are independent and identically distributed. Yeah, and then the Euclidean norm of a vector is computed like this, which is the distance if you represent this vector here as the difference vector between the corresponding points. Okay, and this norm behaves unexpectedly, because we will see that, okay, so once again, if all the features y 1 to yd, all the d features we have are independent and identically distributed, the mean and the variance of the Euclidean norm can be computed as given here. So the mean of the norm, which is more or less the distance of the corresponding points, can be computed here. It's a times dimensionality minus b. A and b are some parameters, some constants actually, depending only on the central moments of order 1 2 3 4. Forget about that. So there are some unimportant constants. So the basic point is it's square root of d plus the order of d to the power of minus 1. So 1 d to the power of -1, and the standard deviation of the norm is again this constant b plus the order of d to the power of 0.5. Okay, and what does it tell us? Well, it tells us that the norm grows proportionally to the square root of d. Well, this is the square root of d actually, yeah. But the variance remains approximately constant, yeah, because I'm sorry, that was bullshit. Sorry, the norm here, the mean, the norm grows proportional to the square root of d. Sorry, that's the point here, of course. Sorry. So the norm grows proportional to the square root of d, because this factor here and this factor here is neglectable, because if d grows, d to the power of minus some constant is always tends to become 0. Yeah, so this tends to become 0 in high dimensional case spaces. The same holds here. So what remains here is for the norm, for the mean, you have square root of d, and here you have a constant. Yeah, so that means the norm grows, but the variance remains constant for large d. Yeah, so in other words, and this is the point here down here, that's the last point here. So if I take the mean of the distances instead of the individual distance, the relative error I make by doing this becomes neglectable, because the variance doesn't grow. Yeah, so the norms grow, but the error, so to say, when I use the mean instead of the individual observations, the individual distances, they grow, but the norm just remains the same. The variance just remains the same. So the relative error remains, relative error becomes smaller, and at some point it is just neglectable. Yeah. And that is known as the concentration problem. So remember again what I told you before. So if I use the mean instead of the individual vector, the error becomes neglectable. In other words, the distances tend to become similar. Yeah? The higher the dimensionality, the more similar are the distances, and that's not a good news. That's not good news, because a lot of data mining methods use distances and neighborhoods to define patterns. So think about K&N classifiers. They use nearest neighbor distances, yeah, or density-based clustering using distances, distance-based outlier detection. The name is the program. Yeah, so you have a lot of methods, data mining methods, that use distances, neighborhood concepts in order to define and derive patterns. And all those methods are heavily impacted by this concentration phenomenon. Yeah? And well, many of those use neighborhoods, and the usage of neighborhoods is based on a key assumption, because all those methods here assume that objects that are similar to an object are in its neighborhood, and objects that are not so similar to an object are not in its neighborhood. And that's how those methods define patterns, derive patterns. Yeah, but now consider this concentration problem. All objects tend to have the same distance to each other. So what kind of impact does that have to a neighborhood? Yeah, so K and N distances are almost equal to each other. How to use K and N distance to classify, or to take that as an outlier score. Yeah, so the K nearest neighbor, that K nearest neighbor is a random object and not really significant anymore in that case. Yeah, so that is a huge impact for all those distance-based methods.